This is part 2 of the lecture on general relativity. At the end of part 1, I described Einstein's eureka moment, his flash of insight, his flash of genius, if you will. With respect to the results of the Gedanken experiment, Einstein realizes that the laser light here at the surface of the Earth, for example, is in fact tracing out a straight line. But it's tracing out a straight line through curved space. In realizing this then leads Einstein to a hypothesis. This is the hypothesis that's at the heart of general relativity. The hypothesis of general relativity is as follows. The presence of mass curves the geometry of space and time. We experience that curvature as gravity. Okay, now here's what this hypothesis is saying. I'm going to show you a version of a classic demonstration of this hypothesis that all introductory physics students see. And that demonstration is as follows. Okay, I've got this felt here. Imagine that the two-dimensional surface of the felt is a representation of three-dimensional space. And then I've got this wooden ball here. Let's think of this wooden ball here as the Earth. The Earth is moving in a straight line at a constant speed the whole time through space because no force is being exerted upon it. In other words, it's just obeying the law of inertia, like so. But now you're saying, okay, well, what about the sun and what about the force of gravity? Well, now I'm going to take this baseball here and let's let this baseball then represent the sun. I'll place it here on the felt. And notice that the baseball is now curving the two-dimensional surface of the felt into a third spatial dimension downwards, like so, forming then what is referred to as a gravity well. Now, the whole time that the Earth is orbiting the sun, it's actually moving in a straight line at a constant speed the whole time. But it's moving in a straight line at a constant speed through curved space, like so, as it orbits the sun. Now, when you see a demonstration such as this, it could definitely be a little bit misleading. Because, for example, I take the baseball and I take the wooden ball, and then after all, I am actually relying on gravity because really all that's happening here, of course, is that the wooden ball is rolling downhill. And then secondly, what's also misleading is the physics of the demonstration itself in the following manner. The two-dimensional surface of the felt here represents three-dimensional space, and then the baseball curves the two-dimensional surface of the felt into a third spatial dimension. What really happens, however, is that the presence of the sun curves three-dimensional space into a fourth spatial dimension that we cannot directly experience. This fourth spatial dimension is a dimension of time. It's specifically the speed of light c multiplied by time. That fourth spatial dimension is given a name. It's referred to as hyperspace. So once again, this demonstration can be a little bit misleading because you're looking at a poor two-dimensional rendition, if you will, of what is actually happening in three-dimensional space. The presence of the sun curves three-dimensional space into a fourth spatial dimension that we don't directly experience. That's the dimension of hyperspace. Okay, now this is a very beautiful, elegant idea, and the reason why is because it now gives us a cause to the force of gravity. Remember the Newtonian picture of gravity. The Newtonian picture of gravity is that gravity somehow acts instantaneously and somewhat mysteriously across empty space, for example, between the sun and the Earth. And that mysterious force then holds the Earth in its orbit as it orbits the sun. We now have a much deeper understanding as to what gravity actually is. Gravity is actually just geometry. It's the curvature of a four-dimensional geometry in the presence of mass. Einstein mathematically develops his hypothesis. When he does, he ends up with an equation. It's referred to as the Einstein field equation. The Einstein field equation describes a four-dimensional geometry that is curved by the presence of mass. Einstein publishes the theory of general relativity in early 1916. Okay, immediately two tests of the theory occurred. Okay, one of those tests was actually supplied by Einstein himself in his original paper in 1916. It has to do with a peculiarity associated with all of the planetary orbits. All of the planets do what I'm about to describe, but it's most noticeable with the planet Mercury because the planet Mercury is closest to the Sun. This is referred to as the precession of Mercury's orbit. Okay, here's what I mean. Okay, first of all, Mercury obeys Kepler's first law of planetary motion. It traces out an elliptical orbit around the Sun. Okay, so for example, let's say right here is an ellipse, and then right here is the Sun. Rather than tracing out this same ellipse over and over and over, however, what's actually happening is that the entire ellipse itself is slowly swiveling or precessing around the Sun. So for example, let's say that we look at Mercury and it traces out the ellipse that I drew here. And then the next time that it orbits the Sun, the ellipse itself moves a little bit or swivels a little bit to the side. It looks, for example, like this. And then the next time that Mercury orbits the Sun, the ellipse looks like this, and so on and so on and so on. The entire ellipse slowly precesses around the Sun. This precession of Mercury's orbit has been known since the time of the mid-17th century. We've been aware of this. We've known about this precession since the mid-17th century. Now you can explain the precession of Mercury's orbit using Newtonian gravitation if there is another object in between the Sun and Mercury that is exerting a gravitational force upon Mercury. For example, say hypothetically, another planet. If there was another planet in between the Sun and Mercury, its gravitational influence, for example, would cause the precession here of Mercury's orbit. Okay, now, every time that there was a solar eclipse between roughly the mid-17th century up until the time of Albert Einstein, everybody would get out their telescopes, for example, during the solar eclipse, and then vainly search the space in between the Sun and Mercury, looking for this hypothetical planet that was causing the precession of Mercury's orbit. Astronomers were so convinced that this planet had to be there that they actually went so far as to give this hypothetical planet a name. The planet's name, the hypothetical planet in between the Sun and Mercury that was causing all of this, was referred to as Vulcan. And then, yes, Gene Roddenberry with Star Trek, he basically stole that name for his fictional universe. But the planet Vulcan was this hypothetical planet in between the Sun and Mercury that was causing the precession here of Mercury's orbit. Suffice it to say, Vulcan was never found. So in other words, Newtonian gravitation cannot explain this. General relativity does. Here's how general relativity explains the precession of Mercury's orbit. Okay, once again, I'm going to use my felt here to illustrate. Okay, as shown earlier, the baseball representing the Sun, that then curves the geometry of space and time around it like so to form a gravity well. However, the Sun itself is actually also rotating on its axis. When it rotates on its axis, it does so with a rotational period of about a month or so. It takes roughly 30 days or so for the sun to complete one rotation. Okay, now I'm not going to use the baseball here to illustrate this. Instead, what I'm going to do is take the felt and then just pinch it like so. And then as the sun rotates, it then causes space-time itself like so to twist in this manner. This twisting, if you will, of space-time is referred to as frame dragging. Einstein works out the mathematical details of frame dragging as the sun rotates. He then applies it to the planet Mercury, and sure enough, the predicted path of Mercury's ellipse matches up exactly with what we see. So in other words, we have now explained the precession of Mercury's orbit by using general relativity, whereas Newtonian gravitation fails. So, general relativity explains this precession as being caused by what's called frame dragging as the sun rotates. Newtonian gravitation provides for us no such explanation. Okay, now that's pretty convincing evidence all by itself that at least Einstein is on the right track with general relativity. However, what is it that turned Einstein into a rock star? What turned him into a media star, for example, the most important figure in 20th century history, and his fame still reverberates to this day? Well, that actually occurred in 1919. Okay, in May of 1919, there was a solar eclipse. Now, the solar eclipse itself is not all that important. However, during a solar eclipse, the moon is blocking the sun, and then therefore you could very easily look at the space that is very close to the sun. According to general relativity, the following should happen. Okay, so for example, let's say that right here is the Earth. Okay, let's say that right here is the sun. Okay, I'm not going to bother drawing in the moon here because the eclipse itself is not important. It's just that the moon is blocking the sun's light, so we can then safely look at the space near the sun. Okay, now let's say way in the background like so, we have a distant background star. And what I just drew right here is the star's actual position in the sky. We know where it is by mapping it out ahead of time, for example. So this is the star's actual position. And then according to general relativity, the presence of the sun curves the geometry of space around it. So now imagine light then coming from that star and passing by the sun. As it does, passes through curved space, like so. And then let's say that we have an observer right here on the Earth. Notice the direction that the observer is looking when that person looks at the star. The person doesn't see the star as if it's here. Instead, the observer is looking in this direction, like so. This is the star's apparent position. Notice that the star's apparent position is further away from the edge or the limb of the sun than the star's actual position. So imagine during the total solar eclipse, you're looking at the eclipsed sun, and then you look at the background stars. The background stars are further away from the sun than their actual position. Newtonian gravitation makes no such prediction of this. So during the solar eclipse of 1919, everybody realized that this was the perfect opportunity to test general relativity. So the background sky surrounding the sun during the solar eclipse was photographed extensively, and sure enough, the stars' apparent positions were not quite in their actual positions. They were further away from the sun according to our line of sight. In other words, general relativity is confirmed. Once again, Newtonian gravitation makes no such prediction. When this observation was published in the world's newspapers in 1919, literally overnight, Einstein became world famous. Because what Einstein did here was he basically recast, if you will, completely our understanding of gravity. So you can start to think of Einstein and Newton in the following way. Isaac Newton in 1687, with the publication in Principia, he basically invents physics as we know it today. And then roughly 250 years later, when you get to Einstein in 1916, Einstein basically reinvents physics, and it turned him into a media star. His fame was the same as the fame that we see, for example, around us today of today's media stars. One of the reasons perhaps why Einstein became so famous when this result was published in the world's newspapers in 1919 is because 1919 was a very bad year for humanity, much like it is here, by the way, in May of 2020. As you're probably aware of already, there was a major pandemic that was going on at the time. 50 to 100 million people worldwide died by the flu between 1918 and 1919. World War I had just ended as well. The carnage associated with World War I was absolutely horrendous. So this was a pretty bad year for humanity, and people were looking for something to cheer about. This was something to cheer about, because here comes Einstein, who basically looks like everybody's favorite uncle, and he basically reinvents or completely revises our understanding of physics and our understanding of gravity. General relativity is a very beautiful, elegant idea. We now have a much deeper understanding as to what gravity is. I'm going to pause here at the end of part 2 of today's lectures.